Response characteristics of structures having irregularity subjected to vertical excitation. Abstract. In India, recent studies on different earthquakes have shown that the structures or building are not designed for seismic loads, and even if the seismic loads are taken into consideration, the irregularities and the effect of irregularities in the structure is skipped. In very general perspective, the buildings are only designed for gravity loads. The IS standards are not taken into account while designing, resulting into higher destruction of the structure when it is subjected to an earthquake. The complex-shaped structures in current-day scenario getting very common due to architectural elegance, but these structure are great threat when not properly designed. In this work, various RC structures are formed having various different types of irregularities in them. All the remaining parameters such as sections of beams and columns, material properties, loading conditions, and combinations, support conditions are common in all structures for a fair comparison. All of the frames were analyzed using standards mentioned in IS 1893 Part 1:2002. By the end result, it's been interpreted the base frame with no irregularity evolves least story drifts, while the structure with floating columns shows maximum story drifts on the soft story levels. Thus, such buildings must be designed effectively, taking proper care of the dynamic behavior of the structure. Keywords: dynamic response, structural irregularity, mass irregularity, stiffness irregularity, open ground story building, step building. Introduction. Irregularities in structures are typical function in today's modern times. Aesthetics of the structure is given a great importance, and thus all planning are done from initial stage of the structure, making the structure irregular. Irregularities in structures makes the structure more vulnerable at the time of earthquakes. At the time of earthquake, the failure starts at the weak spot of the structure, and the weak zone in the structure lies where the mass, geometry, stiffness, etc. changes of the structure. The irregularities in structure also arise due to unexpected change in strength at a specific floor in the structure. Even for an experienced and intelligent structural engineer, it is a difficult task to avoid such conditions. Hence the focus of existing study is assessing the relative performances of typical vertically irregular structures in a probabilistic domain. Due to scarcity of land in large number of structures, ground floor is planned as parking floor, thus making this floor as auxiliary story. Also, the floors above the ground floors are proposed with setbacks for proper ventilation and aesthetic purposes, making it a stepped kind of building. Recent studies have shown that the augs of soft story kind of building have collapsed and has shown negative results when subjected to ground excitations. IS Code 1893 have defined the vertical irregularities within the structure. This irregularities in mainly due to change in height, change in base size, change in stiffness, change in strength and mass of the structure. Thus, in area with high seismic vulnerabilities, it is important to consider the above factors. IS Code 1893:2002 specifies two types of irregularities. 1. Plane irregularities, 2. Vertical irregularities. This study mainly focus on vertical irregularities. Vertical irregularities are of 6 types. A. Stiffness irregularity, soft story, a story having lateral stiffness less than 70% of the above story or less than 80% of the average of above 3 stories. B. Stiffness irregularity, extreme soft story, a story having lateral stiffness less than 60% of the above story or less than 70% of the average of above 3 stories. C. Mass irregularity, when the seismic weight of any story is 200% of its adjacent stories, mass irregularity occurs. D. Vertical geometric irregularity, vertical geometric irregularity occurs when the horizontal dimension of lateral force resisting unit is more than 130% of adjacent story. E. In-plane discontinuity in vertical lateral force resisting elements occurs when the in-plane dimension offset is greater than its adjacent offset dimension. F. Discontinuity in capacity, weak story, when the story's lateral strength is less than 80% of the story above the story is said to be weak story. When these types of irregularities are present in the buildings, the building may be classified into different types as follows. 1. OGS, open ground story. Building in this structure, the ground story is kept open for the use of parking. I.e. no walls are been provided at this level of the structure, thus irregularity is been induced, making the structure less stiff. 2-step building in this structure, the upper floors are proposed with upper setbacks for proper ventilation, aesthetic purpose, and also to compliance with floor area ratio in the building bylaws. 3. Bare frame buildings, usually while developing the building the walls are not erected, thus making the whole structure more prone to lateral loads. In the seismic point of view, this is more vulnerable because lateral load are totally resisted by the bare frame. 4. Infilled masonry building, in this building the frame structure is filled with masonry walls, thus masonry walls transfers the forces in the compressive action acting diagonally in the opposite path to the beams below, thus making the complete structure more stiff. 2. Problem statement. A large numbers of structures are designed to withstand live and dead loads only. Individuals are not aware of earthquake-resistant design of structure even if they are. Most of them avoid taking seismic factors into account while designing. In the seismic vulnerable areas like Zone 4 and Zone V, one must consider earthquake factors. In this thesis, a framed structure having G+9 stories is considered. The structure is intended for the use of residential purpose. The ground story is planned as a parking floor, thus making the structure an OGS type of building. The symmetrical configuration pattern is taken and complete analysis is been carried out using live load, dead load, and seismic loads in the STADD Pro V8i software. 3. Methodology. A 10-story RCC frame is considered in the study. In total 10 frames are been created in which a base frame having no irregularity is compared to all other frames having different irregularities. All the seismic parameters are set according to the IS 1893, Part 1, 2002, and the model is analyzed using STAD-Pro software. The base structure is symmetrical in plan and also is vertical direction having same story height throughout. The structure is 15m x 15m in plan. Abbreviations: L equals earthquake load, DL equals dead load, LL equals live load. B. Arrangements of frames. Arranging the frames as per irregularities and considering the regular frame as the base comparison frame. All the types of frames that are being used are as follows. Figure 1. Ideal base frame. 1 frame 1. This is the basic and 10-story frame having height of 3.5 m and the bay width of 5 m. The basic specifications of the building are: dimensions of the beam equals 0.450 times 0.250 m, column size equals 0.30 times 0.30, beam length equals 5 m, column length equals 3.5 m, dead load equals 12 knots per square meter, live load equals 10 knots per square meter. 2 frame having first and second stories soft. No floor slab has been provided, which makes these 2 stories less stiff, i.e. softer. 3 frame 3. This frame has fourth and fifth stories soft. No floor columns, vertical, have been provided, which makes these 2 stories soft. 4 frame with heavy loading on third and sixth stories. 2 stories of the building, i.e. third and sixth stories, carry heavier loads, hence making the building irregular. 5 frame 5. The frame carries heavier loading on the top story, e.g. in the top story swimming pool has been introduced, hence making the top story heavy, and the building becomes irregular. 6 frame 6. In this frame the intermediate columns are removed, making the ground story soft, and thus an irregularity is introduced in the building. 7 frame 7. The frame is made irregular by removing the end columns and placing the intermediate columns in it. 8 frame 8. This frame has fourth and fifth stories soft. No floor beams, horizontal, have been provided, which makes these 2 stories soft. 9 frame 9. In this frame the geometry of building is changed by changing the height of building in 3 bays and hence introducing the irregularity in the building. 10 frame 10. In this frame, along with geometric irregularity, the intermediate columns are removed. Irregularity is introduced by doing so. All the frames arranged in the above said manner are shown in the figure below. Figure 2 frames 3D view instead. 4 result. A comparison of structure. Every irregular structure is compared with the regular framework and the following variation is seen. The member which are in contrast with the regular structure member are taken into consideration, i.e. the member which are in contrast to base frame members are compared, and shear force, bending moment and axial force tables are formed. V. Conclusion. 1. Considering the story displacement data, the structure and the frame having floating columns, frame number 7 is most fragile because it shows high displacement in top story level. Also form the ground story, it shows high displacement except frame number 2. 2. Considering story drift, the frame and structure having OGS, open ground story, shows the highest story drift at bottom story, thus the structure is more fragile and can result into plastic hinge deformation of columns at ground story level. 3. Frame number 8 shows very similar story drifts as frame number 2 at the mid-height of the structure. 4. When we take story shear into consideration, frame number 4, with third and sixth story major, shows maximum shear. From this it may be concluded that the frame and structure with floating column shows highest displacement, thus are in worse condition and are suspected to fail under current loading circumstances. 5. As we observed every detail regarding the base frame, i.e. the frame number 1, it shows very least drift and displacement, thus is very safe considering other structure. When this frame is compared to frames with soft stories, it is observed that the soft story structures shows highest story drifts. 6. Thus the evaluation demonstrates that the structure without irregularities is safe and the structures with irregularities are unsafe. It is crucial to have regular and simple shaped buildings in addition to even distribution of load throughout the structure.